Let knowledge flow like a river without any hindrance. Don't make it like a stagnant pool. Design and analysis of R.C.C. combined footing of 4 columns with a strip beam as per IS 456. Before start of the lecture, please like, share and subscribe my channel. Hello, I am PS Chatterjee with you. Today I am going to explain how we can make a pro forma in Excel spreadsheet for the analysis of combined trapezoidal R.C.C. footing of 4 columns with strip beam. And this is my last video of this series of combined footing with the strip beam. In this combined trapezoidal R.C.C. footing of 4 columns with strip beam, I am going to consider the moment distribution, and all other basic principles of the design will be the same. But we have to manipulate in our Excel sheet. After grabbing that manipulation, we can solve the problem of combined footing with strip beam and any number of columns. Minimum requirement for this: IS 456-2000, SP 16-1980, Excel software 2010 onward, any standard book. Important clauses regarding trapezoidal combined footing. Dimension symbols and units. Design shear strength of concrete. The design shear strength of concrete is given in the table 19 of the code. The value given in the code are based on the following equation. This tau c is our design shear stress or shear strength of the concrete. FCK, characteristic strength of the concrete. PT, this PT is equal to percentage of steel provided. And this is our table 19. This is grade of concrete M15, M20, M30, M35 and M40 above. This is our percentage of steel provided. For solid slab, the design shear strength of the concrete shall be K tau C. But the value of K is given in this chart. For beam, we should consider the value of K is equal to 1. Maximum shear stress tau C max. Tau C max required for the beam design. And the value of tau C is given in this chart. It depends on the grade of concrete M20, M25, M30, M35 and M40. Now calculation of shear stress in strip beam. Tau C cal. Calculated shear force say VU. Width of the beam B. Overall depth of the beam D. Cover of the beam CO. Effective depth of the beam D underscore EFF is equal to D minus cover minus phi by 2, that is dia of the bar. If tau C cal greater than tau C max, then we have to change the dimension of the beam, or in other words, we have to alter the design. If tau C cal less than tau C, then we have to provide the nominal speed up, that means minimum speed up. If tau C cal greater than tau C but less than tau C max, then we have to calculate the shear force that has to be borne by the stirrups. Shear force that has to be borne by the stirrups, say it is equal to VUS in kilonewton. VUS is equal to VU minus tau C into B into effective depth. Dimensions of stirrups. Say number of legs is equal to N, dia of bar is equal to phi, spacing of stirrups is equal to S. Total cross-sectional area of each stirrup is equal to ASV. ASV is equal to N into pi by 4 phi square. VUS is equal to 0.7 Fy into ASV into effective depth divided by spacing, where Fy is equal to grade of steel, D underscore EFF is equal to effective depth of the beam, SV is equal to spacing required. Or we can write SV is equal to 0.87 into Fy into ASV into effective depth divided by VUS. Moment distribution method. STB1, STB2, STB3, STB4 and STB5 is our strip beam. C1, C2, C3, C4 is our column. L1, L2, L3, L4, L5 are the length of the strip beam. Modulus of rigidity or stiffness of a member denoted by capital K, and capital K is equal to EI by L, where E is equal to elastic modulus of the member, I moment of inertia of the member, C length of the member. Relative stiffness of the member denoted by small k, and value of small k depends on the opposite side support condition. If opposite side support is end support or free support, then K is equal to 3/4 EI by L. If opposite support is intermediate support or fixed support, then K is equal to half EI by L. Say we have 4 columns C1, C2, C3, C4. C1 and C4 are the end columns. So moment from C1 can be carried over to C2 and similarly from C4 to C3, but not in opposite direction. Steps for moment distribution method. Relative stiffness of joints C1 and C4 is equal to 0, since C1 and C4 are the end support. Relative stiffness of left hand side of C2 is equal to K1 is equal to 3/4 EI by L2, since C1 is end support. Relative stiffness of right hand side of C2 is equal to K2 is equal to half EI by L3, since C3 is an intermediate or fixed support. Relative stiffness of joint C3 is equal to K3 is equal to half EI by L3. Since C2 is an intermediate or fixed support, the relative stiffness of right hand side of joint C3 is equal to K4 is equal to 3/4 EI by L4, since C4 is an end support. Total relative stiffness under column C2 is equal to K total underscore 1 is equal to K1 plus K2. Total relative stiffness under C3 is equal to K total underscore 2 is equal to K3 plus K4. Distribution factor of left hand side of the column C2 is equal to dF1 is equal to K1 by K total 1. Distribution factor of right hand side of column C2 is equal to dF2 is equal to K2 by K total underscore 1. Distribution factor of left hand side of column C3 is equal to dF3 is equal to K3 by K total underscore 2. Distribution factor dF of right hand side of column C3 is equal to dF4 is equal to K4 by K total underscore 2. In my problem, I have considered same material and the cross section of the beam throughout. So small k is equal to 3/4 L or half L. Now K total underscore 1 is equal to K1 plus K2 is equal to EI 3/4 by L2 plus half divided by L3. K total is equal to K3 plus K4 is equal to EI into half by L3 plus 3/4 L by L4. dF1 ultimately 3/4 by L2 by 3/4 by L2 plus half by L3. Similarly for dF2 half by L3 by 3/4 L2 plus half L3. Moment distribution chart. This is C1, C2, C3, C4. Relative stiffness 0, 0, K1, K2, K3, K4, 0, 0. Total relative stiffness K1 plus K2, K3 plus K4. Distribution factor K1 divided by K1 plus K2. dF2 is equal to K2 divided by K1 plus K2. Similarly, dF3, dF4. Cantilever moment say plus M1 and plus M2. Now, for stability of this joint, we have to put minus M1. Minus M1 plus M1 is equal to 0. Half of this minus M1 will carry over to this C2 joint, 0.5 M1. Similarly, minus 0.5 M2. Now fixed end moment, WS curve by 12. This is minus M3 plus M3 minus M4 plus M4 minus M5 plus M5. Again, to balance this minus M3, we have to put here plus M3 and here minus M5, and it will carry over to C2 half of plus M3 and minus M5 will carry over here half minus half M5. Starting moment, sum of this, plus M1 minus M1 plus minus M2 plus M2. This is its balance condition. Now, this is also sum of all these moments, Unbalanced moment in this joint C2 and C3, M8 is equal to M6 plus M4, algebraic sum. This is M4 plus minus M7. Now, first distribution M10 is equal to M8 into dF1, and this is M11 is equal to M8 into dF2. Similarly for M12 is equal to M9 into dF3, M13 is equal to M9 into dF3. Carry over. Half of this moment will from M11, half of M11 will carry over to this point and half of M12 will carry over these 2 points. Second distribution. This is unbalanced moment. This is unbalanced moment. So 0.5 minus 0.5 M12 into dF1 minus 0.5 M12 into dF2. Similarly for minus M5 into M11 into dF3 minus M5 into M11 into dF4. Final moment will be like that: minus M1 plus M14 minus M14. This is the sum of all this moment. M15 minus M15 minus M2 plus M2. Now I'm switching over to the Excel spreadsheet for the numerical calculation. Welcome to my Excel spreadsheet for the numerical analysis. These are the load on column C1, C2, C3, C4. And this is our combination working load case. This is equal to this plus this plus this plus this. combination load case. So I'm copying this, copy, paste spatial value. Area required 40.33, but we have provided 29.7. So I'm increasing the width because here column length is fixed. Not sufficient. 3. Now it is sufficient. Our elected load case is 101, that is dead load plus live load. So factor of safety accordingly 1.5. Pressing the control switch, we are selecting this load. Copy, paste. Now, once again, copy, paste spatial value. Distance of column C2 from C1 is equal to 4.77 meter. Distance of column C3 from C1 is 8.770. Distance of column 4 from C1 is equal to 11.770. Along Z direction it is 0. Length is equal to 13.5. Width transverse direction, width is equal to 3 meters. Net reaction in column is same as previous problem. Mx is equal to 0, Mz is equal to this one, and this is distance of Cg from C1, and this is our total load. Now total length 13.5 meters. Total UDL is equal to partial factor of safety, that is 1.5 into this load divided by Lx. This is column load, this load into partial factor of safety. Similarly for this and this. Projection, cantilever projection is equal to Lx by 2 minus Cg distance. And this projection is equal to Lx minus these and this. This is our moment distribution chart. Span moment is equal to WL square by 8 minus WL square by 12. This is our relative stiffness. This is end column. So 3/4 by L1 or S1. This is S1. This is intermediate column. So it will be half S2. Similarly, this is half S2 and this is half 3/4 S3. This is S3. Total relative stiffness, this plus this plus this. Now distribution factor, C2 relative stiffness divided by total stiffness. Similarly, relative stiffness divided by total stiffness. Now cantilever moment, WL square by 2. W is equal to 442 kilonewton. Here L is equal to 0.352 meter. Similarly here, W L square by 2. Now, for the stability of this joint, we have to put here same moment in opposite direction. So minus 27.356 minus here minus 419.236. Now half of this moment will carry over to this point. under seat to left hand side. And similarly, half of this moment will carry over to this point. Now, fixed end moment. This is WL square by 12. This is WL square by 12. To balance this moment, we have to put plus 837 kilonewton meter moment here and minus 419.236 kilonewton meter moment here. So it will nullify this. So starting moment, algebraic sum of all this moment. Now first distribution. This load minus this load plus this load into dfc2. This is dfc2l, dfc2r. I will write. Similarly for this and this. Now half of this moment will carry over to this point. Half of this moment will carry over to this point. Again, we have to distribute. Again, this moment and this moment, half of this moment will carry over to this point, half of this moment will carry over to this point. The process will be continued till this moment is negligible. Final moment, this is the algebraic sum of all this moment. Similarly for this, and this. Now shear force. W into L. W into 0.325. And at the right hand side of this column, C1, this load minus this load. And in this way, we can find out our shear force. One thing we have to keep in our mind that this moment, sign of this moment, plus minus, plus minus, plus minus, plus minus in this way. This portion is STB1, this portion is STB2, this portion is STB3, this portion is STB4, and this portion is STB5. The maximum moment 853 kilonewton meter. Maximum shear force 1084 kilonewton. This is our strip beam number 1. Left hand side of the strip beam number 1 and right hand side of the strip beam number 2. Column under C1. Moment here 27.356 kilonewton meter, and we have provided 5 number of 12 torr plus 5 number of 12 torr bar. A forced of 4-legged 8 torr 50 spacing. Now say here moment is very negligible, so I am concentrating on shear design. Say we are increasing the spacing. Required spacing 55, but we have provided 100, so we have to change. This is the calculation for STB2. Right hand side of the STB2 and left hand side of the STB3. This is our right hand portion of the STB2, and this is our left hand side of the STB3. The maximum moment 853 kilonewton meter. Maximum shear force 122 kilonewton. Say we are changing the depth to 700 mm. The depth 700 is not sufficient, so we're changing to 750 once again. Okay, here spacing required 67, but we have provided 65, so it is okay. If we change it to 100, status of the design will be changed. Check the design. Can't do. Design status. Design is okay. In my last two videos, I have already discussed in detail about the strip beam design, so I'm not going to discuss here in detail. We can design all the strip beam from STB1 to STB5 and for the span moment. Now design of the bottom slab. This is our bottom slab with 3 meters and this is our strip beam with 600 mm. This distance is equal to 3 minus width of the beam divided by 1000, just converting to the meter, divided by 2. And we are going to consider the beam face for the calculation of shear force and bending moment. Bending moment WL square by 2. This is our UDL. This is UDL on beam. This is UDL on plate. This is in kilonewton meter. This is in kilonewton meter square. In this way, I have already explained all this thing in my earlier two videos. Here DE, thickness of the end, is equal to 150, and at the column at the beam face it is 375. If we reduce this value, what will happen? Design is not okay. Undo. If we change it to 16, percentage of steel required, it will cross the maximum limit, PT limit, max. So once again we are changing it to 12. If we change color spacing to 75, design it's not okay. So, but if we change it to 16, now we are changing dia bar to 16. Design is okay. And that's all about my combined footing design with strip beam and 4 columns. If any of my viewers wants to test this Excel sheet, can write to my mail address. It's free. But before writing, read the description of the YouTube. Please don't forget to subscribe my channel and also evaluate my performance with your valuable comments. Thank you.